All right. Here we go. Here we go. Okay, so like charges repel each other and repel, and unlike charges attract each other. So these two forces, and this is what we do, is we just draw the forces where they are on the line, and then we see if they're repelling if they're like charges, or if they're attracting if they're unlike charges, okay? Nothing too hard there, all right? Charged objects and electric force. Okay, this is kind of how ink. So you're a salesperson for the right fit. But anyway, I don't even know why that's in there. Not only can an electric charge. Oh, wait, I got way ahead of myself. Is that all they have? Contact by induction. Oh, sorry. Conductors and insulators. I forgot to talk to you about all this stuff. Okay. Charged objects and electric force. Okay, so not only can electric charge exist on it, but it can also move through an object, just kind of like heat does. Negatively charged, then moves to the positive charge. We kind of talked about all this stuff. Substances that are readily conduct electrical charge are called conductors, and things that also conduct heat well are the same thing as things that can usually conduct electricity well. All right. Materials that do it poorly are called insulators. Okay, this is what we're charging by contact. Metal sphere, so he knows what happens. The charge is set up on the sphere. Then they all form on the outside, just like we saw in John voltage. So I was talking about all this stuff. I just thought, I don't know what I was thinking. Okay, so this is charging by induction. We get the rod close, and then here's what happens. Oh, and then here's what it shows you when it runs to ground. Then you take them both away, and it's positively charged. So there's your slide for that little quiz question, and we did that. All right, an eminent rod, positive charge. This is the way the balloon worked on the surface. Remember? Okay. Now we're to Coulomb's law. All right. So here we go. Notice, this is the way we'll do it. We'll just draw two charges, and it'll tell us if one's positive, one's negative, or it'll tell us where the forces are pointing, and we'll decide. We'll go, if the forces are attractive, then we'll know, oh, wait a minute, this is probably good chance that this is a negative, a positive and a negative charge. If they're repelling each other, it's positive and negative. And here's Coulomb's law right here. Q1 and Q2 over R squared. All right. He used 8.99. I used 9.00. It doesn't matter. And this echo knot, this permittivity of free space, we will look at later when we look at capacitors, but it's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. All right. And we also give it a different amp per area also type thing. Okay, so that's called the permittivity of free space. It's just a physical constant out there, kind of like Newton's thing. It's just what it is. Permittivity, I don't know what it means. They could have called it the electric gook or gunk. I don't, it's just out there. Okay, model of a hydrogen. You actually have a homework problem like this. Here is, in the Bohr model, the electron is in orbit about the nucleus. Determine the speed. This is a great problem. Let's do this problem. This will be fun. We're going to do this thing together. All right? And then we're going to look at some of your other homework problems. But let's do this problem to start with. And then we'll start with the electric field in the next lecture. All right? So in the Bohr model, the electron is in orbit about the nuclear proton. The radius of 4.9. So let me write down all the things that we have here. Notice this is at a positive E and this is at a negative E. How the heck are we going to get the speed of the thing out of this? Well, this is a force. It's going in a circle. This is the Bohr model, remember. The new model that you've learned from Goodnev, of course, is completely different, of electrons in clouds floating around. But this gave us the start, and it's also actually pretty accurate for a hydrogen atom. It's not bad. All right, so let me write down R is equal to 5.29 times 10 to the negative 11 meters. Okay, that's the radius that they're apart. I know the charge of a proton is 1.6. I'm writing all this down, times 10 to the negative 19 positive coulombs. Charge of the electron is equal to negative 1.6 times 10 to the negative 19 coulombs, but I'm not going to worry about that. The mass of the electron is equal to 9.11 times 10 to the negative 31 kilograms. Mass of the proton is equal to 1.67 times 10 to the negative 27 kilograms. So I got everything I need. All right, I've got everything I need. So let's take a look at what I'm doing here. On page 5, your notes. All right, so we want to know, here's my proton here in the middle, here's my little bitty electron out here, okay, and here's the distance r, and this, what's its speed? What's its, oh, it's the centripetal force. Remember that? The centripetal force is equal to mv squared over r, which in this case, the v squared over r, which is equal to ma, which is equal to the mass times the force of the, which is equal to mass, which is equal to the electric force. Aha! Which the electric, so I've got mv squared over r is equal to k times q1 over q2 times q2 over r squared. I get some dinky numbers here. All right, so I wind up with v squared is equal to k times q1 over q2. If I multiply both sides by r, then that r goes away and that one gets canceled, over v over m. And so this is equal to, basically this is equal, v is equal to the square root, of k q squared, because we're doing the absolute value. So we'll just take k q squared divided by the mass of the electron, which is what's moving around, times that radius r. Whoa! So what I'm going to do is, I'm going to go ahead and do the mass of the electron, or I'm going to do kq squared. So I'm going to get, and I'll show you how I do it on the calculator. 9 second e to the 9th, there's k, times 1.6 second e to the negative 19, and I'm going to square that. All right, and then I'm going to go ahead and compute that, and there it is. Then I'm going to divide that second answer divided by parentheses, parentheses, and I'm going to put the mass of the electron in here, which is 9.11 second e to the negative 31. And then I'm going to put in, notice how I did it by itself, double parentheses, so that there's the mass of the electron. Mass of the electron is right here. Now I'm going to put in that distance of 5.29 second e to the negative 11, double parentheses again. So I've done the top part, and I'm dividing here. And now watch, I'm probably going to get a number that's greater than the speed of light. It is. It's 4.88 times 10 to the 12th power. But that's in meters squared per velocity squared. That's the square root. If I take the square root of this thing, second square root, second entry, bang! I get basically 2.2 times 10 to the 2.2 times 10 to the 1, 2, 3, 4, 5, 6. So the velocity is equal to 2.2 times 10 to the 6th meters per second, which is less than 3.0 times 10 to the 8 meters per second, which is the speed of light. So I'm in good shape. All right, that was fun. Let's see if we're correct. I rule. All right, that's Coulomb's law. Okay, determine the magnitude and the direction of the net force on Q1. Let's figure out what Q1 is here. Okay, so notice, you figure out this force here. which is going this way. You figure out this force here, which is going that way. Now, I will always give you one-dimensional problems like this. So let's just watch how this one's done. Yeah, let's watch how this one's done. Then in the next one, I'll go to your homework problems because I think we're ready. Okay. So here's what they did. They said, all right, so the force on 1 caused by 2 is equal to Q1, Q2. So notice what they did. They did it all positively. And they wound up with 2.7 newtons because it was the force on 1 caused by 2. So 3 times 4 microcoulombs. Notice they put in the microcoulombs. Came up with 2.7. And then, since it's all in a straight line, they subtracted it. Now, these are vectors, and so they go into this kind of stuff, which I don't do to you on the problem. And I definitely won't do it to you on the exam. All right. So let's go look at the homework problems for this, and we'll be done with lecture 1.